Okay, in this video we're going to finish up section 1.9 from our notes, and this is the last section that's on the first exam, where we're going to talk about onto and one-to-one linear transformations or mappings. And I know it's been a minute, so let me just remind you what we're talking about here. So we had previously been talking about linear transformations, and the idea is, in this particular example, this linear transformation takes boxes and shears them, right? It deforms the box in some sense. And so if we were talking about doing this to an image, it would deform it in that way. And so we had sort of talked about linear transformations in class as being similar to maybe what Snapchat does when you take a picture of yourself and it alters the image in some way. So that's how we're thinking about what a linear transformation is. Now, mathematically, linear transformations satisfy these two properties. So, and we're going to use one of these in class today. And so the first one says if we apply the transformation to the sum of vectors, you can split it up and apply the transformation separately and then add them. And if we apply the transformation to a vector times a scalar, you can pull the scalar out front. And so that's sort of mathematically what a linear transformation does. And that's important in general because the other thing we talked about was all linear transformations can be written as a matrix. And so that's what this says. Every linear transformation can be written as a matrix times the vector that you're applying the transformation to. And this is, we talked about how you find that matrix. That's sort of what we had done in the last class, where we found the matrix representation of all these various transformations on the next several pages here. Okay, and so that's sort of just a quick reminder about what a linear transformation is. And now what we want to do is talk about one-to-one and onto transformations, or mappings, if you will. And so on this page, this first part is talking about onto. You can see that this first definition is about what onto means, and then the one at the bottom of the page here is talking about what one-to-one means, and so we'll go through them one at a time and then look at a couple examples of these types of transformations. And so let's read the definition. So right here it says a mapping T, and remember we read this means it sends things from Rn to Rm. We say that that transformation is onto Rm, and you can see Rm corresponds to the place it's going. If each b in Rm is in the image of at least one x in Rn. And so, just as a quick reminder, because we're going to use this word in a second, Rm in this case, which is the place where the transformation is sending vectors, we call that the codomain. And so in these two images down here, this is showing a transformation that's not onto, and this one is onto. And let's explain why each one is or isn't. So in this particular transformation, this is taking things from the domain, which kind of looks like a two-dimensional piece of paper, and it's sending things to the range, which also looks like a two-dimensional piece of paper. But you can see that the codomain, which is Rm, is actually a larger space, and the range only occupies a subset of that space. In other words, this is true. The range is a subset of the codomain. And if you've never seen this notation before, this little kind of C-looking thing means is a subset of. And so this one's not onto because it takes things from this set and it sends it over to the range, but the range is not filling up the whole space. Right? But this one is onto because in this particular case, this domain, this is the domain, this is the range, right? And you can see that the range and the codomain are the same space. So the range equals the codomain in this one. In other words, whatever the codomain is, it gets filled up by this transformation and the range becomes the entire space. And so I want to write that down in words right here. So T is onto if it, the way I think about it is if it covers or fills up all of the codomain Rm. The other way to say that is this range, everything in the range is the entire codomain, right? So let's focus on this one. The range here is only a piece of the codomain, right? So this piece of paper that is the range is a subset of the larger space that is the the cube. Where this one, the range and the codomain are the same exact size, right? They're the same space, and so that's what makes it ON2. So let me write that down a different way. That is, another way to say that would be a transformation is ON2 when the range of T is all of the codomain. And so, in other words, everything in the codomain here is hit by something from T that's getting sent from the domain. But everything in the codomain here is not hit by T, which is sending things from the domain. So, sort of the way we test for this is, if we want everything to have a solution, which is in the codomain, which is the case here, we need to have a pivot in every row. And that's not going to be the case here. And so practically, T is going to be ON2 if there's a pivot in each row of the matrix representation of the transformation. And so that's how we test for ON2 if we have the matrix representation, is we row reduce the matrix and see if we have a pivot in every row. Okay, and we'll go into a little more detail about that on the next page. One-to-one is a different but related characteristic of a linear transformation. So let's read this. So a mapping from Rn to Rm is said to be one-to-one if every b in the range is the image of at most one x in the domain. And so let's look at the pictures. Again, this is a not one-to-one. This one is one-to-one. And so we see the domain over here, the range over here. So this one's not one-to-one because we have two different images here, and there's several things being sent to that image. Right? So we have like 3 dots over here in the domain, and each one is getting sent to the same place in the range. And so you have things that are not one-to-one because you have more than one thing in the range coming from the domain. Things are one-to-one if you have this situation where everything in the domain gets sent to its own location in the range, right? If you look at these images in the range, every dot comes from just one thing in the domain. And so let's write that down in words and talk about how we test for it. So another way to say that is, we say that a transformation is one-to-one. And you might remember this from pre-calc. I teach this in pre-calc, and it's a similar concept as pre-calc, except we're talking about matrix multiplication and linear algebra instead of just regular functions in R. Anyway, that is, T is one-to-one if every vector in the domain, so it would be the left side of these pictures, is sent to a unique location in the range. As is being done in this right-hand image. Sort of the other way to say that is something's not going to be one-to-one if you have two separate things being sent to the same location. And so let's write that mathematically. So T is not one-to-one. I like to abbreviate one-to-one with 1-1 just to be clear. If there exists some image in the range, so some b in the range, such that the following happens. Two things get sent to b, and so that means T of x equals b, and T of y equals b, where x and y are not the same thing. So this is saying you have two different things in the range, x is not equal to y, and they get sent to the same place in two different things in the domain get sent to the same thing in the range. So that would be an example on the left there. And so, the key to this in terms of testing for it is that the unique thing, right? So it gets sent to a unique vector. Well, we have unique solutions if we don't have free variables, right? Or the other way to say that is when we have a free variable, we end up with infinitely many solutions, which means non-unique. And so to test for one-to-one, we look for free variables. So in practice, we're gonna say T is 1 to 1 if every B in the range, I need to white that out. If for every B in the range Rm, T of x equals B has a unique solution. And what that means is no free variables. So just like everything else in linear algebra, you know, when we test for 1 to 1 and on2, we will reduce a matrix. And for on2, we look for a pivot in every row. And for 1 to 1, we look for a pivot in every column, because that would mean no free variables, right? And so that's what we're thinking about here. And we will shoot this over to the next page and look at an example and a couple theorems, and I'll ask you to think about one as well. All right, I'm going to flip the page. Feel free to pause it if you need to finish writing this down. Okay. So here's the example that we're going to look at first here. So we've got a matrix representation of a linear transformation. In other words, we're just being given a matrix here, but we have a transformation T of x, and it equals AX, where A is this matrix, right? And so let's think about where this is taking things from and sending them to. Let's start there. So T is a transformation, and let's think about where it's taking things from and where it's sending things to. So we'll fill in some numbers there in a second, but let's think about how this works. So, you know, in order to do this transformation, you multiply by this matrix. And so A is a 3 by 4 matrix. Excuse me. And so if A is 3 by 4, you need to multiply by things that have 4 elements, right? Because if you did AX, you need the inside dimensions to line up, and so we would need it to line up with this thing. And so this, in other words, the number of columns, 4, tells you where you're coming from, it tells you what the domain is. And so this means you need to multiply by vectors in R4. And then, since it has 3 rows, that means the result ends up being 3 by 1, right? So this 3 tells us that things are sent to R3. And so just looking at the dimensions of the matrix, we see that things get sent from R4 to R3. So there's an R4 right here, and it gets sent to R3. Just looking at the dimensions there. And so we're going from a bigger space, R4, into a smaller space. So you can imagine things being filled up in that space, so it's possible things would be on 2. It's not possible to go from a smaller space to a bigger space and be on 2, but it is possible to go from a bigger to a smaller. And then the opposite is true with 1 to 1, right? If you have all these things in R4 and you want to send them to R3, you're going to have to hit some of them twice usually, and so it's probably not going to be possible for this one to be 1 to 1, but just sort of thinking about it practically is one thing. Let's show it mathematically. And so the question here is, does it map R4 onto R3? So this is the on2 question. We'll do that first. And then the second question is it 1 to 1? We'll do those sequentially down here. So first step is to look at on2. I would draw a line down at the bottom there, maybe about 3/4 of the way through the page, and we'll do 1 to 1 separately. Okay, so like the previous image shows us, if something's on 2, then it fills up the entire codomain. The range fills up the codomain. And so if that's the case, that every vector in the codomain should get hit by one of the vectors in the domain. And so let's pick a vector in the codomain, which is R3. So let B be in R3. The idea is that if A is on 2, then that means every vector in the domain, in the range, every vector in R3, in the codomain I should say, so for every vector in R3, there has to be some vector in R4 that hits it. So there must be an x in R4 such that ax equals b. And just to be clear, we're sending things from R4, so this x is a 4-dimensional vector, and then it gets sent to a 3-dimensional one. And as I sort of phrased this on the last page, the other way to think about this is that the matrix A hits all the vectors in R3. Right? That's what I just wrote down. Every single vector in R3 has to be the solution to one of these transformations coming from R4. The other way to say that mathematically is that ax equals b will always have a solution. i.e., the real question here is, does ax equal b always have a solution? And again, b is in R3, and so I'll say for all vectors in R3. That's what this question is asking us, right? If it's on 2, the answer is yes. If it's not, then the answer is no. And so we know how to solve equations like this, right? We want to see if ax equals b has a solution. And so the answer is going to be yes if this is always true, if this is always a consistent matrix. And we know this is a consistent matrix if we have a pivot in every row. And so the answer to this question is going to be yes if the matrix AB has a solution. In other words, is consistent. We know a matrix is always consistent if it has a pivot in every row. i.e., again, if there's a pivot in every row. That's what we're looking for on 2. We want there to be a solution to every single ax equals b, and there's always going to be a solution, i.e. always consistent, if there's a pivot in every row. And so let's row reduce this thing. And actually, if we notice, it's already in REF. Right, so there's a pivot right here, down right pivot, and so this is in REF. It's not completely reduced, but it's in REF. And so let me just rewrite the matrix down here, and then we'll answer the question. So I'm going to rewrite this matrix right here. 1, minus 4, 8, 1. 0, 2, minus 1, 3, 0, 0, 0, 5. And then I'm going to add a final column here and just say, put some fake vector in there, b1, b2, b3. Because I want to see if this system's consistent for every single possible b, and so I'm just going to write an arbitrary vector down and see if it's consistent. And again, here's a pivot in that row, down right, there's a pivot in that row, down right, there's a pivot in that row. And so if I want a solution for this entry, you get it from this pivot, right? If you want a solution from this entry, you get it from this pivot, and if you want a solution for this entry, you get it from this pivot. In other words, it's always consistent, right? You don't have a 0 plus 0 equals not 0, because you have a pivot in every row, and so this transformation is on 2. So A has a pivot in each row, i.e. it's consistent. Always, not just sometimes, it's always consistent because we always have a pivot in every row. Thus, we always get a solution for ax equals b. Thus, there is always a solution to ax equals b. For every possible b, right, we just have an arbitrary b in there, and that means, by definition, T maps R4 onto R3. So let me write that. So T is on 2, and more specifically, T will map R4 onto R3. In other words, it takes things from R4 and then it completely covers up every single possible vector in R3. There's always going to be a solution to AX equals B, no matter what B we pick, because there's a pivot in every row. And so kind of looking back to the image on the last page here again, this would be, going from R4 to R3, and the entire range fills up the codomain. Okay. I will then look at 1-to-1. And so 1-to-1 means that every single vector in the domain gets sent to its own vector in the range. And so let's start thinking about what that means and what the answer is here. So question 2 is it 1-to-1? Well, if it is, then there should be a unique solution to AX equals B, right? So if T is 1-to-1, and I don't need to see all these details on homeworks and tests and things. I'm trying to write out all the words and things so it makes sense. And so you can go back and read it later. I'm a little too zoomed in here. Just noticed. I hope that hasn't been a problem. Okay, it's a little bit better. So if T is 1-to-1, then that means every vector in the domain, in the codomain, the domain, in R4, the domain, is sent to a unique, and that's the key word, unique, vector in R3, the codomain. However, we can very clearly see, just looking at this one more time, this same reduced version, right? X3 is a free variable. We can see X3 is free right there. And so we have a free variable, and so that means we can't have unique solutions. And so this is not 1-to-1. So in this particular case, here, X3 is a free variable. Just looking at the matrix above, we can see that very clearly. And so that means when you do A times some vector, you're going to have a free variable, and it's going to have infinitely many solutions. And if there's infinitely many solutions, they're not unique, obviously, right? And so that means Tx, which is represented by the matrix A, is not 1-to-1 in this case. Just to be even more clear, it would be if there was no free variable. Okay. So for on2, we need to have a pivot in every row. 1-to-1, we need to have a pivot in every column, no free variables. And so that means only square matrices can be both 1-to-1 and on2, right? If you want a pivot in every row and a pivot in every column, like if we deleted that column, it would be 1-to-1, for example. And so it needs to go from the same space to the same space in order to be both 1-to-1 and on2. If we want to be on2, going from a bigger space to a smaller space is possible, or between the same space, but not vice versa. And if we want to be 1-to-1, then you need to be going from a smaller space to a bigger space, or the same size space. Otherwise, you'll have multiple solutions, which means no free variable. A free variable. Okay, I'm happy to answer some questions about this if you guys have them moving forward here. Let's look at a couple theorems related to this, and then ask you to think about one on your own here. So one result that we get from these ideas is the concept that, let me just fix my camera here. Okay. Okay, so one thing we see is that a linear transformation is one-to-one if and only if, so this is an if and only if statement, if and only if the transformation equaled 0 has only the trivial solution. And so I'm going to prove this right here, and this is an if and only if statement, and so it means it's double-sided, right? So if you have a one-to-one transformation, then t of x equals 0 has only the trivial solution, and if t of x equals 0 has only the trivial solution, then it's one-to-one. So it works both ways, and so the way that you prove statements like this is you prove them both directions. And so we'll prove it going forward. In other words, we'll assume it's one-to-one and then show that t of x equals 0 has only the trivial solution. And then we'll prove it backwards as well. We'll assume that only the trivial solution exists and then show it's one-to-one. That's how you prove that both sides of the implication exist. So on the first direction, let's suppose t is one-to-one. So let's say it's a linear and one-to-one transformation. So we're assuming the first part is true, and then we're going to try to prove that the equation t of x equals 0 has only a trivial solution. Well, this uses one of those properties I showed you right at the beginning here. Let me just flash that back up here, which is this. Nope, I lost it. Here it is. So we previously showed on this page that if we have a linear transformation, then this must be true. And so we showed this previously on this page, and so I'm not going to necessarily do it again, but let me just say that, let's just write that down. So since, suppose it's linear and one-to-one, since t is linear, t of 0 equals 0. And I'm just going to put C notes since we already covered this part of it. And we know that, so we know this is true from the fact of being linear. If we know it's one-to-one, then they can only have one possible solution, and so it must be the trivial solution, since the trivial one always exists, right? And so since t is one-to-one, then t of 0 equals 0, that was something we assumed that it was one-to-one, must have only one solution, and we know it must be the trivial one. And so we've assumed t is one-to-one and linear, and then we've showed that t of x equals 0 has only the trivial solution. So we knew that t of 0 equals 0 from previously, and since it's one-to-one, it must be the only one, since by definition there can only be one. For the other direction, we assume the other part. We assume t of x equals 0 has only the trivial solution, and then we'll show that t is one-to-one. This is a little bit more of an interesting proof than the last part here. So let's assume the second part. So let's suppose t is linear, and let's suppose t of x equals 0 has only the solution x equals 0, the trivial one. And let's do a proof by contradiction. So what we're going to do here is we're going to assume this part's true, but then we'll assume that t is not one-to-one. So we'll say, well, let's assume that this part is true, but t is not one-to-one, and then we'll show that that leads to something that can't be true, which will show that t must be one-to-one. So we're going to assume the thing we're trying to assume here, and then we're going to see what happens if t is not one-to-one. Okay, so let's suppose t is not one-to-one. We'll show that this leads to a contradiction. So if t is not one-to-one, then there must be two vectors that get sent to the same place, right? So that means there exists two vectors, let's call them u and v, such that they're not the same, they get sent to the same place. So T of U equals T of V, which equals some vector B. Right, that's the definition of not being one-to-one. Two different vectors getting sent to the same place. This leads to a contradiction because of the following. But if we did T of U minus V, we know again from the same property here, right? We can split this up into two separate things. And so this would be T of U minus T of V. And in this case, they both equal B, so it's B minus B, which is 0. But we just said that it only had the trivial solution. So in other words, U minus V gets sent to the 0 vector, but we just said that it only had the trivial solution, and U minus V is not equal to 0 because U doesn't equal V, right? So we're sending something, U minus V, to the 0 vector, where U minus V is not 0, since U doesn't equal V. And so this is a contradiction because we assumed that the only thing that gets sent to 0 is the 0 vector, but then we just showed that something else gets sent to 0 that's not the 0 vector. And so this is a contradiction. And so, in other words, T of x equals 0, we just found has a non-trivial solution, which is a contradiction. This contradicts our original assumption. And so that means T must be 1-to-1. And just to be clear here, from here to here what I did is I used the property of linearity by breaking up that difference there. And so that's a much more interesting, I think, part of the proof here. Again, we showed it both directions. We showed if it's 1-to-1, then T of x equals 0 has only the trivial solution. And then we showed if it has only the trivial solution, then it must be 1-to-1. And again, that was a proof by contradiction, which is a very, very common, typical proof strategy that we use in mathematics. You see that being taught in math thought and other upper level math classes where proof is involved. Okay, please let me know if you have some questions about that. I'm happy to answer either one of those. Any questions about the proof at all? The other theorem I'd like to just share with you is sort of extending the inverse matrix theorem a little bit, and we'll add some more things to the inverse matrix theorem shortly. But this is sort of emphasizing again how everything in linear algebra is very much tied to each other. And if you have a strong understanding about row reduction and free variables and what the implications of those things are, then most of these things should just follow sort of naturally from each other. For example, let's say we have a linear transformation, and let A be the standard matrix for T. So in other words, T of x equals AX, right? Well, this says we have an onto transformation if and only if, again, this is a double-sided implication, the columns of A span Rm. And then the second one says we'll have a 1-to-1 transformation if and only if, again, double-sided implication, the columns of A are linearly independent. So how, I'm sort of telling you something new, but you should really be thinking, oh, I kind of already knew that. So let me explain A, for example. So A is talking about onto. It's saying we'll have an onto transformation if the columns of A span Rm. Well, we previously showed that the columns of A span Rm if there's a pivot in every row. And that's the definition of being onto. Right? So A, we previously showed that A will span Rm if there's a pivot in each row. And this is the same definition of onto. So in other words, it should make sense that onto and spanning Rm are the same thing. They have the same, you test for them the same way. The second one is talking about free variables again, right? So we showed previously that if we have linearly independent columns, there's no free variables. Well, if there's no free variables, we just said that that means A is 1 to 1. And so it's just sort of linking these things together, right? So B is saying, we previously saw that the columns of A are linearly independent if there's no free variables. And this is the same definition as being 1 to 1. Okay, so again, everything in linear algebra, or at least most things, lots and lots of things, are highly interrelated, and if you know one thing, you can sort of link it to lots of other things and learn lots about a given matrix or transformation or whatever the particular topic is. Alright. The next thing I usually do in class is have people work on a problem together and just sort of think about it, and so I'm going to ask you to think about this next problem, this example, on your own. But please do think about this one. So here is a linear transformation represented by some matrix. And so again, in this particular situation, we're thinking about some linear transformation acting on vector x, and it equals A times that vector x, where this A is the matrix that we're given, right? And so A is a 3 by 3, right? And so it takes things from R3 and sends them to R3 as well. And so this particular transformation, we could say, it takes things from R3 and sends them to R3. Again, because those are the dimensions of A. That you multiply by things that are 3 by 1, and they end up being things that are 3 by 1, so that's why it's 3 to 3. So based on the last couple pages, we see that we're looking for free variables and pivots, and so we want to row reduce this matrix to see whether it's onto or 1 to 1. And so I'm just going to go ahead and write down the row reduced version. It's worth trying on your own. You should know how to do that with a calculator. But when you use a calculator to do row reduce echelon form, you obtain the following. And so I would like you to just take a second and think about the implications for that with respect to 1 to 1 and on 2. I'm not going to sort of like leave a dead space in the video here. I'd ask you just pause the video, look back at the last couple pages, see if this makes sense. It's really on you to sort of try this on your own. Hopefully you're taking this seriously and you will give this a try, and just pause it real quick and think about whether or not the transformation is 1 to 1 and or on 2. And in just a minute here, I will start filling out the answer, but again, please do take the time to treat this like a normal class and put yourself out there and see if this makes sense. Okay, so I'm going to start the solution. Hopefully by now you have taken a second to think about this. So when I'm looking at this matrix, I see there's a pivot right here, down right, there's a pivot right here, there's a mobile pivot in this last row, and so we see that x3 is a free variable. And so just based on those two things, we already know what's going on here. So the first question, is T on 2? Well, if we wrote this matrix down and we want it to equal a B, so let me just do that real quick. So I'm going to rewrite the reduced matrix down. And we want that to equal some arbitrary vector in R3. So I'm going to do x1, x2, x3. Well, this is a problem in the last row, right? This is why we need a pivot in every row to be on 2. If x3 is not 0, we're going to have an inconsistent matrix. And so this is not on 2, because if we want some solution to the last entry, we're not going to get it with this matrix. So this is inconsistent when the third entry is not 0. And so, in other words, excuse me, since row 3 has no pivot, it's not on 2. So let's just write that down. So since row 3 has no pivot, right, it's all zeros, the matrix is going to be inconsistent when we don't have an entry of 0 in the third spot. Thus, T does not map R3 onto R3. In other words, you might be saying, well, what the heck do you mean? It takes things in R3, but then it maps to some subset of R3. So it takes things in R3 into a subset of R3. And you know, you might be wondering, what the heck does that mean? Well, let's actually think about what the solution of this is. So the answer to the onto is no, it's not onto because we're missing a pivot in the final row here. But let's be more specific and look at the solution. I'm going to write the solution down right here. Solution to this system, if we wanted to solve this, it's going to have a single free variable in it. I don't want to... I guess what I'll say is the solution has a single free variable. We can't write the solution down because it doesn't have a solution, right? This is inconsistent. But what I want to mention is the solution has a single free variable which means T will span a one-dimensional subset of R3. In other words, your answer is going to have a single free variable in it, and so there's going to be one element in the basis, which we haven't talked about quite yet either, and so that means that we're mapping to, like, we're taking things in a cube and we're mapping them to like a line inside the cube is what we're thinking here. So that's clearly not onto because it would fill up the entire space if it was. As for one-to-one, the free variable tells us it's not one-to-one either, right? So in order to be one-to-one, we need to have no free variables. We've got a free variable in x3, and so T is not one-to-one because we have a free variable. So let me finish that last part. So T 1-to-1 question mark. So x3 is a free variable, so no. And I'm going to write down a little bit more than that just to kind of clarify it, but so x3 is a free variable, so x3 is a parameter in the solution. And so that means there's infinitely many solutions, which means it can't be one-to-one. In other words, AX is not unique, and that means the matrix A or the transformation T are not one-to-one. Again, because we've got that free variable. And so, you know, I've tried to spend some time here talking about what one-to-one and onto means, sort of some visual things, why the tests come out the way they come out, and why we look for free variables or pivots to sort of test for these things. But in practice, testing for them is pretty straightforward, right? If you want to look for onto, you see whether or not there's a pivot in every row. So pivot in every row. If you want to look for one-to-one, pivot in every column, right? Free variables. And so testing for them is easy. I'm trying to build the intuition behind why we test for them in that way, so you don't have to memorize things, right? If it just makes sense, you don't have to memorize it. The last thing I just want to close with in this particular section is, I hypothetical application. And so, I mentioned Snapchat a bunch of times, and certainly, when you do Snapchat on your phone and it manipulates an image, there's certainly a linear transformation going on there. But here's sort of another way to think about linear transformations in an applications type setting. So let's say we had two pictures of Edgerly, which is the math building at Fitchburg State. Here's a matrix or a picture of Edgerly from straight on, and here's the same image or the same building just from an angle, a different angle, right? You can tell it's the same building though, just maybe this picture is taken from over here or something. Now, we might be interested in knowing whether or not we have two images of the same thing, if we're not familiar with it, say, or we want the computer to decide it. And so let's say we want to write a computer program that determines if the two images are of the same building. Then the goal of the program would be to determine whether or not the two images can be aligned using some linear transformation. And so what we would do, just hypothetically speaking, is we would take each image and make it into a matrix. And so we call that, going from here to here, discretizing it. And that's a very common thing with image processing. I've got a bunch of applications that I work on as well that take images or maps of the applications I work on and make them into big matrices. So you can see when you discretize it, each one of those entries could represent, say, like a color value or something like that. And then you basically have a matrix representation of your image. And so if this is our matrix A, you can see, this might be our matrix B. And we would want to know, can we manipulate this image and make it look like this image, or vice versa? And so we could try to find a linear transformation that would allow the two matrices to align. In other words, can I find some transformation that takes this matrix and transforms it into this one? That's what this is saying. This is just sort of a hypothetical problem setup. It's not actually a solution to the problem, of course. It's just sort of talking about, it's framing the problem in a linear transformation type setting. And there's lots of these types of applications out there outside of just Snapchat or fun things. This is just sort of a hypothetical setup of a potential problem that uses linear transformations that we would need some more tools to solve, but I hope it gives you an idea of how linear transformations are applied. Okay, we're also going to move into section, chapter 2 here, section 2.1. This is not on the first test, of course. This will be on our second test and also on the final. But we've sort of built enough of a foundation in linear algebra and row reduction and solving systems where we can now talk about some more advanced topics like matrices themselves. And so we're going to start by talking about multiplying matrices, and we first need to sort of remind ourselves about some of the terminology here. So first of all, this is a general matrix, right? We say that matrices are size m by n, and so the m refers to the number of rows, and the n refers to the number of columns. And so you can see that just if we go down here, right, it goes 1 I m, so there's m rows, and then there are n columns, right? This is the nth column right here. Each individual entry we denote with a sub ij, and so you can see that just in the individual entries here, right? Like this is a11, and the I and the j refers to the row and the column. So the I is the row number, and the j is the column number. Right, so this is a11 because it's in the first row, first column. This would be amn because it's in the last row, last column. Okay, that's just good because we want to refer to specific elements. For example, the diagonal elements, those are going to be the ones where the I and the j are equal. So for example, a11 is on the diagonal because it goes right down through the middle, right? a22 is on the diagonal, a33 is on the diagonal, etc., right? Like a12 will be on the diagonal, etc. And so just kind of visually speaking, I realize I'm zoomed in a little too much here. There we go. So visually speaking, the diagonal would be these elements right here. Right? They start in the upper left-hand corner, and then you go down right, down right, down right, and those would be the diagonals. So these are the diagonals of this particular matrix. So with that in mind then, a diagonal matrix is specifically square whose non-diagonal entries are 0. And so diagonal just means that the only non-zeros are on the diagonal. For example, a 2 by 2 diagonal matrix might be something like this. We can see that that's diagonal because there's non-zeros on the diagonal. They could be zeros on the diagonal, but the point is the only non-zeros are on the diagonal. Just to kind of drive it home, a 3 by 3 diagonal matrix might be something like this. Again, that's diagonal because the non-zeros, again, are on the diagonal entries. Let's just do one more, a larger one, and show you that you can have zeros on the diagonal. So this would be a 4 by 4 diagonal matrix. And I'll go ahead and just throw a row of zeros in there. Just pointing out that, yeah, this is supposed to be a 0 right here, is on the diagonal, but the point is the only non-zeros are on the diagonal. That's what makes that matrix diagonal. Okay. Great. So let's see here. We're going to talk about adding, subtracting, multiplying matrices. So you can add matrices. So the first section here is obviously sums and scalar multiples. So when you have two matrices that have the exact same dimensions, so the same number of rows, the same number of columns, then you're allowed to add or subtract them. Very similar to the way we do adding and subtracting with vectors. You just add or subtract the exact entries. So here's an example here where we have two matrices. They're both the same size, right? So these are both 2 by 3. And so that means we are allowed to, it's possible to add or subtract them. Now, very similar to with vectors, you just add or subtract the specific entries. And so that's why you need to have the same number of them so that you can have something to add or subtract from every entry. So for example, a plus b, I will do the gruesome detail here. You just do like 1 plus minus 3, for example, or you do minus 2 plus 1. Etc. So it would be 1 plus minus 3 in the first entry. The second entry would be 10 plus 4. The third entry is minus 6 plus 6. This entry is minus 2 plus 1. This one's going to be 5 plus 0. And this is minus 1 plus minus 7. And, you just simplify that down, and so this is the matrix minus 2, 14, 0, minus 1, 5, and minus 8. And so you just add or subtract the individual entries. Take a second and pause the video real quick and think about a minus b. See if that makes sense to you. So you would just do the same thing, except you subtract the individual entries. Again, pause the video real quick. I will start writing down the answer. Write down the answer and check to make sure that you got this one correct. So when you subtract the entries, you should get this. Okay. So adding and subtracting matrices is very easy, just like it is with vectors. Similar to vectors, adding or multiplying by a scalar is also very easy with matrices. When you multiply by a scalar, you just multiply every entry by the scalar, the exact same as you do with a vector. So, as a quick reminder here, scalar, that word just means it's a constant. So for example, 3 times A, if you wanted to multiply this matrix A by 3, you would just take each one of these entries and multiply it by 3. And so that would be 3 times that matrix. Again, each one of those entries gets multiplied by 3. And so we end up with 3, 30, minus 18, minus 6, 15, minus 3. Let's look at a theorem related to this. So this theorem is basically telling us that we can change the order in which matrices are added, and we can change the way they're grouped. These are very typical things that exist with numbers too, right? So this is saying you can change the order in which you add matrices. This is telling you can regroup the order in which you add them, right? If you add a zero matrix to A, it stays the same. This is a distributive property, so in this case R is a scalar, right? And so in this case this is telling us you can distribute a scalar to the sum of two matrices. And similarly, if you have a sum of two scalars, you can also distribute the matrix through there. Right? So basically, matrices have these nice distributive, associative, commutative type properties with addition and subtraction. It's not the case with multiplication, which we'll see pretty soon. And so note that nothing in here has anything to do with multiplication. It's just telling us we're allowed to rearrange the order in which matrices are added or subtracted. Let this focus here. Okay. But also notice that, and I think I've talked about this before, when we talk about matrices, and it says right here, notice that we're using capital letters for the matrices, and we use lowercase letters for individual scalars. And that's usually always the case in linear algebra, where we represent all matrices with a capital letter. And scalars are usually lowercase. So for example, like when we're going to talk about matrix multiplication, it's talking about the matrix A, B. And so A and B are each separate matrices. We know they're matrices because they're capital letters, right? So in this particular description down here, A is a matrix, some random matrix, B is some other matrix. Again, we know they're matrices because they're capital letters. Okay. So it says, and we've talked about this before, recall that for the matrix A times B to be defined, the number of columns in A have to match the number of rows in B. Furthermore, the resulting matrix, A times B, has dimensions rows of A by columns of B. So, for example, here we have a matrix A and a matrix B, and we're being told A is 3 by 5, B is 5 by 2, right? And so you can see that this is 3 by 5 because it has 3 rows, 5 columns, and B is 5 by 2 because it has 5 rows, 2 columns, right? The first number is the number of rows, the second is the number of columns. And so in this particular example, if we multiplied A times B, then A is a 3 by 5, B is a 5 by 2, and we see that their inner dimensions match, right? The 5s match. They match, you can see. And so that means we're allowed to do the multiplication. So since they match, you can do the multiplication. And that means the resulting matrix is going to have this dimension. So you line up the number of rows in A with the number of columns in B, and that tells you the resulting size of A times B. So A times B is going to be a 3 by 2 because A has 3 rows and B has 2 columns. And so if these numbers didn't match, we would not be able to do the multiplication. And so that's what happens if we try to do B times A. Right? So B times A, notice what would happen. If we did B times A, that would be B is a 5 by 2, A is a 3 by 5, and so these inner numbers are not going to match, right? The 2 and the 3 are not the same. So that means we can't do this multiplication. What you'll see is we end up doing linear combinations of rows and columns, and so we need to have the numbers match in order for them to match up and be able to do that multiplication. And so in this particular one, if we tried to do B times A, we would say the inner dimensions don't match. And so that means B times A is not defined. It's undefined, or does not exist, or something like that. Can't be done. Okay. So, let's talk about how we actually do that with matrices. How do we actually multiply matrices? That's the next step here. That's what we are about to do. actually sort of, you can see here it says the shortcut for matrix multiplication. There's sort of a long cut in the book that talks about doing linear combinations of rows and columns, like I mentioned. And this is also very confusing. It's saying like the I comma j entry for the product A times B is this, right? Some linear combination of the rows of A and the columns of B. See how the I is in the row spot and the J is in the column spot? And that's what it says here, right? To obtain the specific entry A, B, I, J, you multiply the rows of the row I, of matrix A and column J of matrix B. Now, we can talk about that different ways, but it's just helpful to kind of cut right to the way we actually do this in practice. And so that's what I'm going to show you here, is how we do this in practice. Let's multiply A times B right down here. And so we are going to multiply the rows of matrix A with the columns of matrix B, but here's how we actually do it. So here's A, here's B. A times B is going to be a 3 by 2, right? This one has 3 rows, 2 columns, and B is a 2 by 2, 2 rows, 2 columns. And so these inner numbers match, and so that means we can do the multiplication. And then the outer numbers, 3 and 2, is going to be the size of the resulting matrix. And so A times B is going to end up being a 3 by 2 matrix. And the way we actually do that, when we do A times B, it kind of looks like this. There's matrix A. There's matrix B. And so we want to multiply the rows of matrix A with the columns of matrix B, but it's kind of confusing looking at it like that. Okay, but just, A times B is literally that. But the way you actually do that is you take the matrix A, so you make this little, little chart here. And you put the matrix B up here and the matrix A down here. I think I want to move this down just a smidge, though. Should have thought this through a little more. We've got more room, and I'd like to didn't give myself enough room to write the matrix down. So give me just a second here. Let's get this fixed for us. Okay, so we make this little chart. Well, I'm going to write the matrix B right here. 1, 3, 2, minus 1. And then I'm going to write the matrix A, so this is B. I'm going to write the matrix A right over here. 4, minus 2. This will be a minus 3. Minus 3, 0, 3, 5. Now I already know AB is going to be a 3 by 2 from what we said right here, right? And so I know what's going to go into this spot. This is going to be the product that we put in here. It's going to have 3 rows, because it's the number of rows of A, and 2 columns, because that's the number of rows at B. So I know my AB is going to be here, A times B, and it's going to be a 3 by 2. 3 rows, 2 columns. And that's why we stack, where we put the matrices like this, because you can see this one has 3 rows, this one has 2 columns, and the way you do the multiplication is the first column multiplies the first row. So you kind of like do this kind of thing, like the 1 is going to end up multiplying everything in that column, and the 2 is going to multiply everything in this column. And then you do the same thing with the 3. And I know that sounds confusing, but what we're doing is this. And the way that we can do it with this chart is, this entry right here, the first entry in the upper left-hand corner, lines up with this column, and it lines up with this row, the first row. And so that's why we multiply the first row times the first column. And so I'm going to do, write out all the details here to hopefully make this clear. So this first entry is 4 times 1 plus minus 2 times 2. And then when we go down to the second entry, let me get another color here, the second entry lines up with the first column still, and now it lines up with the second row. And so we're going to dot this row with this column. And so this entry is going to be minus 3 times 1 plus 2 times 0. Let me rewrite it just in the right order so that makes a little more sense to us. 0 times 2. And then the third entry here, this entry lines up with this row and that column. And so we dot this row with that column. So it's going to be 3 times 1 plus 5 times 2. And those are that's the first column of the product. And we'll do the second one in a second here, but just clear, we're applying this rule, and more specifically, if we wrote it out in words, the entry ABIJ is obtained by multiplying row I of A with column J of B. And that's exactly what we're doing here in this chart, and that's exactly what the definition says at the top of the page. And so let's finish up here. So, and then this entry lines up with the first row in A and the second column in B. And so we're going to dot this row with that column. And so this is going to be 4 times 3 plus minus 2, 4 times 1, no, 4 times 3 times minus 2 times minus 1, excuse me. This entry lines up with this row and that column, so this is going to be minus 3 times 3 plus 0 times minus 1. And then the last entry lines up with this row, the last row, and the right column. This is going to be 3 times 3 plus 5 times minus 1. And so again, we're dotting the ith row of A with the jth column of B to get entry ij. And so when we do all this and we add up the numbers, we do those multiplications and the sums, we get 0, 14, minus 3, minus 9, 13, and 4. And that is the product A times B. So we just multiplied matrices A times B, and we obtained that product right there. Finish up with the last page, and then we'll finish this section in the next video here. But it is helpful to talk about these properties of matrices. These properties here are very, very similar to the properties we saw 2 pages ago with addition. So it's doing these same kind of things on page 2, except with multiplication, right? So it's telling us we can change the order in which matrix multiplications are grouped. Oh, notice that all these things are capital letters, all A, B, and C, right? So those are all matrices. I should have started there, right? The thing that's lowercase, this R, is the scalar, and it says that right here. Anyway, sorry, so it's saying you can change the order in which matrix multiplication is grouped. You can distribute matrices, right? So you can do this kind of thing where you can multiply A through B plus C to get A times B and C. You can change the order in which you're grouping scalar multiplications and all kinds of other similar multiplication properties. But notice that changing the order of matrix multiplication is not in here, and moreover, in general, notice this. This is really important. And so let me maybe make a note up here before we go down here. What I was trying to say here is, note first of all that you can't change the order of matrix multiplication. And that's particularly interesting because you can usually change the order on those things, right? Like here's the addition thing, right? This is telling us A plus B is the same thing as B plus A. You don't have that here. You don't have A times B being the same thing as B times A. In fact, it's usually not the same thing. And moreover, really matrix division isn't a thing. So there's kind of a lot of things to cover here. So the first thing that I'd like to mention is this. You cannot change the order of matrix multiplication. For one thing, if they're different size matrices, one of those things won't even be defined, right? Here we saw A times B you were allowed to do, right? A times B resulted in a 3 by 2 matrix. But then we said, hey, when you change the order, you can't even do that matrix multiplication because the dimensions don't match. So the first thing to note that is if A and B have different dimensions, one of those multiplications won't even exist. So one of AB or BA won't even exist. Not possible, doesn't exist, undefined, whatever you want to say. Moreover, the second point here, cancellation laws don't hold for matrix multiplication. In other words, if AB equals AC, a lot of the times people might say, oh, well, the A's could cancel, right? You could divide both sides by A and then get B equals C. But what this is saying is it's not true in general that B equals C. So you cannot, like, divide by A. Similarly, if you multiply two matrices and you get 0, it's not true that one of them is the 0 matrix. So I already explained 1. Let me explain 2 really quick. So what number 2 is saying right here is it's saying if you have AB equals AC, you can't just divide by A, and so it's not true that B equals C. And what number 3 is saying, it's saying if you multiply two matrices and get 0, the 0 matrix, then that means you can't divide by A or B to show 1 is 0. And so sort of the big takeaway here, the thing that this box is really trying to tell us here, is that matrix division isn't a thing. You cannot divide by matrices. We'll talk about sort of the matrix version of that, but in general, matrix division is not a thing. It's not possible. It's not something we do. You multiply by inverses, which we'll talk about in this later in this chapter, but you cannot divide matrices. Okay, I think the last thing I'm just going to finish up with, I'd like to finish this page and just give you an opportunity to try two of these, but this is sort of driving home the point above. Here's A, here's a matrix B. Let's calculate, they're both 2 by 2, right? So they're both 2 by 2, so we can change the order of multiplication on them. But let's change the order of multiplication and show that we don't actually get the same thing. And so what you should just sort of take a second and see if this makes sense is multiply A times B, multiply B times A, and when you do that, you should see that the output is not the same. And so I'm going to set this up. This would be A times B. This would be B times A. They're both 2 by 2s, right? 2 by 2, 2 by 2, 2 by 2, 2 by 2. And so since they're all 2 by 2s, that's what lets us be able to change the order, because the inner dimensions are always going to match, because they're all the same, right? And so you can do those multiplications, but what you'll see is when you do the two multiplications, you're not going to end up getting the same thing, which means you can't change the order of matrix multiplication, because that does not commute. And so the way we would set this up, like we talked about on the last page, is you put the second matrix here, the first matrix here, and then you know, this is going to end up being a 2 by 2.
And so you would multiply this column with this row, and then down here you multiply this row with that column. And so you should take a second and try this yourself, right? So this is the whole point of this section, is learning how to multiply matrices. And so you should take a second and finish this up. And see whether or not you get the correct answer here when we actually do multiply these two things together. And so pause the video real quick and try this. Maybe while you're doing that, if you're a little confused, so I'll talk it through. But this entry, like I mentioned, you dot this column with that row and you would get the number 2. Right? 4 times 1 is 2. 2 times negative 1 is minus 2, so we do 4 minus 2 is 2. Right? This entry is this row with that column, so you do 3. 3 times 1 is 3, plus minus 1 times 1, minus 1 is 1, and so you have 3 plus 1, that's going to give you a 4. I'm just going to fill in the rest of the entries here. Please come talk to me, send me a message, set up a time to talk if you're not able to get these values, if these values don't make sense to you. And so this one here is A times B, this one here is B times A, and we can just notice that they're not the same thing, right? That matrix is not the same as that matrix. And so notice A times B does not equal B times A.